you keep torque constant and move time to peak torque, or whether you keep time to peak torque constant time to peak torque constant and torque constant varies. What is the effect of forward displacement of the center of mass? We've modeled all this as well, and basically you see here that when you move the center of mass 2 centimeter or 4 centimeter forward from the malleolus, then what you do is basically increase the total ankle torque required to stabilize the body, and as well as the effective stiffness. But I won't go into these details. So what this shows is that obesity really adds a temporal constraints to the postural control system. It increases the ankle torque required to stabilize the body, and this could increase the risk of falling. Well, obviously, this paper was fairly well received when we published it, but most people told us, oh yes, but that's only a model. So we were collecting data at the same time with obese individuals and asking the simple questions with real people. Is there a relation between balance control and body mass? So the method was quite simple. We simply recorded postural oscillations with a force platform with and without vision for 59 males. They were from 24 to 61 years old and with a BMI of 17.4 to 63.8 kilogram per meter square. And those are some of the results. I present CP speed as a function of weight. The top panel is with vision, the bottom panel is without vision. Each simple symbol on the curve is actually the mean data of an individual, and what you see is clearly as the weight increases you have an increase in CP speed both with and without vision. When you try to explain the variance with this model and you add age in the equation, age adds only 3% to the explained variance. So what it shows is basically that weight is a big factor explaining the increased CP speed in these individuals, the increased oscillations, and presumably the decreased balance control. Those were all males. Do we see the same pattern with other populations, for instance, older women? We looked at that more recently with older women from 65 to 80 years old. We had 3 groups, 15 individuals in each group. One group was they were healthy weight, one was overweight, and one was obese. And again, their task was quite simple: stay upright on a force platform. Here I have CP speed again, and what you see with vision and without vision, the same basic result. Normal weight individuals sway at a slower speed than obese individuals, and obese individuals sway at a slower speed than overweight, and overweight sway at slower speed than obese older women. The next slide is actually in French, but it's basically the data from with the measurement technique that Piero Morasso adopted, where we look at the main duration within stability zone and the mean duration within the stability zone and the mean distance between these stability zone. And basically you see the same pattern, whether it's with eyes open or eyes closed. Let's see, I'll explain it with eyes closed. Basically you see that normal weight older women spend more time in stability zone than obese women, and the distance between these stability zones is shorter, indicating more stable postural behavior than obese older women. So for older individual, what this says is that obesity may be a risk factor for falling that has not been considered close enough. There are quite a few obese older individuals, and obesity, we believe, is an important risk factor for them. So if obesity increases the CP speed and presumably decrease postural stability, reducing weight should increase postural stability. So that's what we look in obese and morbidly obese individual. Again, a very simple protocol, but complex to run. We had control subjects that we tested twice. Obese individuals that lost weight with a hypocaloric diet over an average of about 6-month period, and morbid obese individuals that went through a bariatric surgery and lost up on average 71.3 kilograms. They were tested again, I think, with about a year in between both testing period. Again, CP speed with vision, the control group at baseline and after intervention, no difference. The obese group at baseline and after intervention, a decreased CP speed, and the morbid group at baseline and after interventions, a greater decrease in CP speed because they lost more weight. This is with vision. This is without vision. And an interesting observation, if you look at the obese group and the morbid group after intervention, they were now about the same weight, and they sway about the same. This is simply to show that there was a relationship between the amount of weight these individuals lost and the increase or the decrease in CP speed or the increase in stability. And the more weight these people lost, the greater the decrease in CP speed was. And this was both with and without vision. So there's a strong relationship between weight and balance control. The heavier the person, the less stable the person is. And losing weight improves balance control, and the more weight you lose, the greater the improvement. Now, I'll present some data about strength and non-specific training because people argued with us that, well, perhaps it's because you did not train these individuals, you did not provide them with some training during the weight loss program. So it could be that if you trained them, these people would sway less and would be more stable. So the key questions was basically, are obese individuals less stable because they are weaker? First, we looked at muscle force and force control after weight loss in the obese and morbidly obese men. Basically, in this study, these individuals were asked to produce some maximal force with various muscles, and also we tested their capability at maintaining a given force level for a period of time. I won't present these data, and actually I'll go fast. I'll present only maximal force of the quadriceps femoris, and what we see is basically before weight loss, morbidly obese individuals were actually quite strong. obese as well. They were actually stronger than control individuals. Obviously, when you normalize all this per kilogram, morbidly obese individuals are a bit weaker after weight loss. Basically, you see that morbid individuals lost a lot of force, but they did increase their force per kilogram when you normalize per weight. So what this says is despite the decreased absolute force, we observed a decreased COP speed. So this suggests force is not really a key factor explaining balance control deficit in obese subjects. And actually, a lot of people have argued that before. Fitzpatrick, for instance, and Piero Morasso as well have suggested that we need about 3 to 5% of our maximal force to maintain our posture when we stand upright, when we're not perturbed. So 3 to 5% shouldn't be a factor for these individuals. We also ask, people kept asking us, well, yes, but maybe it's because these individuals are not trained. If you train them, maybe they'll sway less. So we ask, we could have trained these individuals, but we thought it would be simpler to take a group of individuals that are actually heavy and sometimes obese, but already train themselves. We are in America. We have an American football team at my university. Some of these guys are quite big and they train a lot and they're quite strong. So we thought we could use them for a study, and that's what we did. So basically, these individuals were actually younger than our obese and our control groups. They were about 23 years old, while our obese were 37 years old. Their percentage of fat was actually quite smaller than that of the obese groups. They had only 23% of their mass which was fat, while for the obese groups it was about 32%. And these individuals had a BMI which was actually a bit higher but not different than that of the obese group. So they had the BMI of 35, while the obese group had the BMI of 34. So our athletic group was actually younger, had less fat, and a BMI not different from that of our obese group. They were tested during the off-season, that is during summer. During this period, these individuals go through training anyway. They go through non-specific training, mostly 3 cardiovascular training sessions per week and 3 resistance training sessions per week. Our obese and control groups were both sedentary individuals. So in terms of strength, here it's again the quadriceps femoris. If you look at the athletic group, they are much stronger than both the obese and the control groups. They are actually twice as strong. And even in relative strength, they are actually stronger than the control group and much stronger than the obese group. So if strength and training is a factor, these individuals in the athletic group should sway less than the obese group. I have CP speed here for the control, heavy athletic and obese individuals, both with and without vision. And what we see is basically that the heavy athletic individuals sway pretty much like the obese, both with and without vision, and they sway more than control group. So it's not a matter of strength, it's a matter of weight. We have the same results if we look at simple measures of range, and also if we looked at other measures which I won't present. So for normal quiet standing, muscular strength has a minimal relationship with postural sway, and overweight is the important constraint for balance control. Related issues to these results is basically some questions that may be important to look at. What is the effect of a sudden increase in the mass of an individual? For instance, when using a baby carrier or a backpack, this increases the load we carry, and this could increase the CP speed and the instability. Aging also has a negative effects on balance control, and we also know that with aging there's an increased weight gain in most people. Does this increased mass has a deleterious effect on balance control? We believe this is the case. Okay, so next I'll present some data on goal-directed upper limb movements. As I mentioned, balance control is the basis for most of our upper limb movements. So if we have an unstable base of support, then upper limb movements should be affected by this. So obese individuals, when they perform upper limb movements, then these upper limb movements may be less precise than those of normal weight individuals, and this could have some important effect on the task they're actually performing. Some of this work was inspired by two old Frenchmen that devoted most of their career looking at how voluntary movements are actually a source of postural perturbations, and those individuals are actually Jean Massion and Simon Bouisset, which I still meet once in a while and still enjoy a great deal talking with them. So the first study we conducted with normal healthy weight individual. I want to present some of the data just to show you the overall method. It's basically looking at posture and movement and looking at how posture affects the actual difficulty of a movement. For this, we use a classical FITS task where subjects had to point to a target. The FITS task is basically you change the width of a target, and by changing the width of the target, you actually can manipulate the difficulty of the task. So the smaller the target is here, the greater the index of difficulty, which is basically calculated by taking the log base 2 of 2 times the amplitude of the movement divided by the width. So in this particular case, we had 4 target widths going from 3.6 bits to 6.9 bits. 6.9 bits is the smallest target width, 0.5 centimeter, and the most difficult target width. And the target of 25 centimeters is actually the easiest index of difficulty, 6.9 bits. So we had the normal subjects do this task to point at the target as fast as possible in a standing position and in a seated position where the actual target was actually moved downward and was constant with respect to their arm and upper body. A constant position with respect to their arm and upper body. So the main constraint was basically the different posture, upright or standing. What do we see? Movement time is the actual measure to document the difficulty of the task. So we have movement time on this axis and the index of difficulty, the smallest target, the largest target, the smallest index of difficulty, and the smallest target and the largest index of difficulty for both the standing and the seated condition. And what we see is movement time increases with an index of difficulty, but we see also that when the index of difficulty is high, the standing condition leads to a much longer movement time, and we see it in the movement time and in the deceleration time as well. So this indicates that the difficulty of the task is greater when people are standing than when they are seated. Why is this? I'll go fast, but this is a little bit of the story to explain this. Here I have the elbow angle variation against the hip angle variation when seated or when standing for the smallest index of difficulty and the largest index of difficulty. So if we look at the seated condition first, what we see, each trace is a single trial. Those trials are for the same subjects when the subject was seated and when he was standing. And what we see is basically an increase in the hip contribution to the pointing movement when subjects are standing. When they go to the standing position, an increase in the hip contribution when the difficulty of the task increases. And when subjects are standing, this increased hip contribution increases even more. So basically what we see is that as the task increases in difficulty, subjects adopt a movement control where there's a greater hip contribution than the elbow contribution. So this may explain why the balance constraint affects the task difficulty. So if this is the case, then obese individuals, if they are less stable, should have more difficulty and should show longer movement time. So this is what we looked at in a paper published in International Journal of Obesity, and this is exactly what we observed for results. Here we have movement time as a function of the index of difficulty, and we see that as the difficulty increases, movement time increases more for the obese individual than for the normal BMI individual. So obesity increases a great deal the task difficulty. We see this effect is observed both in the acceleration phase of the movement and in the deceleration phase of the movement. And on the next slide, I'll walk you through it. I have basically the CP displacement as a function of the CP speed for an obese subject and for a normal BMI subject. Each trace is actually a single trial, so those are from a representative obese subject and a representative normal BMI subject. And what we see when the subject points to the target, this is the start of the response, is basically a backward movement of the center of foot pressure with a negative speed, followed by a positive speed when the subject moves forward, and this part here is actually the deceleration part of the movement, and this is basically where we see a major difference between the obese and the normal BMI subjects. It's as if they have difficulties decelerating their body while they move towards the target, and this may explain why their movement time is much longer. It's not only a matter of increased mass to the upper limb, as in a different experiment we looked at the effect of a diet program on these movements when subjects were seated and when they were standing. And when you looked at their performance, at the performance of an obese individual when seated, you see that there's no difference in their movement time in the seated conditions. But when they're standing at baseline, that is when they were overweight, their movement times are longer than after the diet program. So this basically, again, shows that obesity adds a balance control constraints. This increases the difficulty of controlling upper limb movements, and it's not the simple consequence of an added mass to the moving limb. There's a similar experiment by a different group in Belgium with children. This is a simple but quite neat experiment, I thought. They use a simple task, which is the Purdue Pegboard Task. This task is really an old task where you basically simply pick up a peg with one hand, move this peg and take it with the other hand, and place the peg in the board at the other end of the board. The task is simply to displace as many pegs as possible in 20 seconds. So what they did is tested 8 to 10 years old children that were normal weight, so a BMI of 16, overweight with a BMI of 20, and obese with a BMI of 25. They tested these children while they were standing and when they were standing on a narrow beam. And those are the performance, the number of pegs that were displaced for the normal weight children, the overweight children, and the obese children. And what you see in the seated and standing on the narrow beam condition. And what you see, particularly when standing on the beam, is a decreased performance from the normal weight to the obese, to the overweight, to the obese individuals. So these very simple results suggest again that obesity perturbs the fine motor coordination in children, and this effect is more important when a postural constraint is present. Are these anecdotic results? Perry et al. A few years back showed that obese children 6 to 11 years old show a higher risk to suffer from injuries to anterior teeth, presumably because of falling. So why do obese individuals weigh more and are less stable than normal weight individuals? There are actually two hypotheses we've been working on. One is an increased output variability. The other one is a decreased sensitivity of the mechanoreceptors. I'll present both right now, and basically the first one, which is about the balance motor command variability, is a modeling study. I'll go fast, but basically what this study is all about is we know that variability in the motor command increases with an increased magnitude of the command. So it could be that the increased COP speed for obese individual is actually associated with greater variability in the balance motor commands. So to look at this, we use a feedback control model inspired from the work of Christophe Maurer and Bob Peterka. It's mostly my colleague Martin Simoneau who did this work. I won't go into all the details, but basically we modeled the variability, and we have a neural controller that basically determine a signal error between the body angle reference and the reference of the actual pendulum, and produces a center of foot pressure and a center of mass in output to produces a torque, and we use the center of foot pressure and center of mass as an output of the model. So those are modeling curves that were obtained for control, obese, and morbid obese individual. We have both the COP and the COM curves across time, and you see that basically these oscillations or these COP and COM measures resembles biological signals. Actually, when we compared the model data and the experimental data for the mean COP speed for both the controlled, the obese, and the morbid individuals, we had a fairly good correlations between these values, and fairly good correlations between the ankle torque and the COP speed that was produced. The main results is basically this one, which is the range of net ankle torque, and you see that for the morbid individuals, there's a greater range of net ankle torque and greater range of variability. So what this study shows is, compared to controls, the faster COP speed of morbidly obese and obese individuals imply larger balance motor commands variability, and we were able to model this. Now, what is the sensitivity of the plantar mechanoreceptors during normal postural controls? Our hypothesis was that with the increased weight or the overload, there are more of these mechanoreceptors that are excited, and this could actually saturate the signal, the sensitivity signals that these individuals receive, and as such provide a less accurate mapping of where they are in space. To test this, initially we used normal weight subjects, all males. They had a BMI of about 24, and we had the loaded conditions where they actually were loaded with the 23 kilogram weight vest, training weight vest, which increased their BMI